Hey everybody, welcome to tutorial 16. This will be a continuation of the previous video, so we're going to pick up where we left off, develop some more synth defs, and touch on a few other ideas that we can use in the context of a short composition. In the last video, we coded this multi-purpose bandpass filtered sawtooth instrument, but one thing it doesn't do is process sound files. So for the sake of variety, let's build a synth def that's capable of sound file playback. On the desktop, I've prepared a folder called Buffers, which contains 3 subfolders of crotales, desk bell, and shaker sounds. We will deal with this entire collection of audio files a little bit later, but for now, we're just going to focus on these 3 sustained shaker sounds. So let's boot the server and just read these files into buffers, simply using 3 buffer.read statements, which we saw in tutorial 8. Remember, you can drag and drop a file into the editor, and it gets converted to a string representing its file path. So what I want to do here is construct a synth def that plays a buffer, applies an amplitude envelope and stereo panning, and optionally routes the sound through a bandpass filter. And for me, a bandpass filter seems like a sort of desirable choice here because with a high quality filter, the narrow filter band makes it possible to bring out one particular frequency, which is going to allow us to apply harmonic or melodic ideas to our otherwise unpitched shaker sounds. So we'll start with a fixed length envelope generator with attack, sustain, and release segments, also giving ourselves the option to control the curves of the attack and release segments. And we're going to use playbuff as our buffer playing UGen. Now, I happen to know that all my sound files are monophonic, as we can verify with num channels. So the first argument of playbuff should be a 1, and then the buff num and the rate argument. And remember that playbuff treats this argument as a ratio, so 2 is twice as fast and 0.5 is twice as slow. Multiplying the rate argument by buff rate scale, as we saw in tutorial 8, is not absolutely necessary, but it's a safe thing to do because if your audio files have been recorded at a sample rate that's different from the SuperCollider server sample rate, buff rate scale will compensate for the difference. And this means that a rate value of 1 will always play back the file at normal speed. And since I'm not planning to change the buff num while the synth is running, it's perfectly reasonable to use the IR method, which is a little bit more efficient, although it should be noted that the difference in efficiency is probably very small, and KR would work just fine as well. I'm also going to specify a value for playbuff's start position, in case we want to start playback from somewhere in the middle of the file instead of the beginning. Notice that the envelope has done action 2, not the playbuff. And this is because I'm envisioning the envelope generator as the governing amplitude process. And we're going to multiply sig and env together later on. And so when the envelope finishes, we have silence, regardless of whether playbuff has been able to get through an entire sound file. So at the end of the envelope, there's no reason to keep the synth running any longer. So done action 2 gets rid of it. To add the bandpass filter, we use xfade2, which is an equal power crossfade UGen, and this is going to enable us to smoothly balance between the unfiltered signal and the bandpass signal. This 4th bandpass filter argument is the amplitude of the filter, and just like we saw in tutorial 14, I'm creating an inverse relationship between reciprocal quality and amplitude, and this provides a boost in amplitude to compensate for the loss in amplitude that results from a narrow filter band. The third argument of xfade2 is the crossfade mix between the 2 signals, where -1 favors the first signal, +1 favors the second, and 0 is a 50-50 crossfade. And actually, I prefer to specify a range between 0 and 1. So what I'm going to do is multiply this mix argument by 2 and subtract 1. And mathematically, this converts my preferred range of 0 to 1 to xfade2's expected range of -1 to +1. Apply the amplitude envelope and apply the stereo panning. And this is where I also like to add a master amplitude argument and output the signal. And finally, of course, we need to declare all of these arguments that we're using. So, only specifying which buffer to play, our synth-def sounds like this. Now, over the years, I've gotten in the habit of adding .buffnum, like you see here, but it's worth noting that you don't actually need it. By default, the attack and sustain times are 0, so we immediately begin a 3-second release. But we can specify a different envelope shape. For example, here's a very short segment pulled randomly from somewhere in the first half of the buffer. Or we can increase the attack and sustain portions for a more gradual amplitude shape. BPF mix is 0 by default, but if we specify a value of 1, we take the unfiltered signal out of the mix completely and instead only hear the output of the bandpass filter. And let's say a center frequency of 2000 hertz. And now we're going to gradually increase the filter quality. With higher quality values, we start to hear a sort of ringing sound that bandpass filters are capable of. Varying the playback rate will play the file back faster or slower, but it won't have much of an effect on the pitch we perceive because the pitch is being governed by the frequency argument. So now let's randomize which buffer to play and also randomize the attack and release times. And for the filter frequency, I'm going to specify an A Lydian pitch collection, making sure, of course, to convert to cycles per second. And I'm going to include a possible transposition up 1 octave. And also let's give some random values for quality and playback rate and panning. Now, even though in our synth-def we are compensating for the loss of amplitude that results from the filter, if you were looking at the level meters, you might have noticed that this is still a relatively low-level signal. So I'm going to boost the amplitude values a little bit above 1. And generally, this is an okay thing to do as long as you're paying attention to the level meters and gradually increase these amplitude values rather than suddenly jumping up to some huge value, which is not a good idea. And maybe as a final touch, we can use iteration to generate many of these synths all at once. Certainly, we could keep playing around with the synth-def and tweaking it, and if you're following along, feel free to do so, but I'm actually going to call this done, and now turn our focus to our collection of sound files. We've only read 3 files into SuperCollider, but as you can see, we have quite a few more, and I think whenever you're dealing with sound file playback, you ought to devote some attention to effectively managing your sound file library. So to give you a sense of what's actually in here, in Crotales, we have a pair of simple hits. and the others are a crotale disc being struck while resting upside down on a break drum. The desk bells folder was featured in tutorial 8. It's just a simple 1-octave chromatic scale. And shakers, in addition to the 3 sustained sounds we've already heard, includes several short sounds. So what we'd like to do is read all these sound files into buffers, ideally using an efficient programming style that allows us to easily and intuitively access individual sounds. Since the focus here is on composing a piece, the first thing I'm going to do is create a project folder. I'm going to call it tutorial piece. And this is where we're going to store all our composition-related resources, because having everything all in one place is nice and convenient. So let's save this current SuperCollider file in this project folder, and also move our buffers folder in there as well. As we saw just now, and in tutorial 8, the most basic way to read a sound file into memory is with buffer.read. With 1 or 2 files, I think this approach is fine, but of course when lots of files are involved, which is often the case for me, this approach becomes very tedious and inelegant. And what's worse is if you add new audio files or take some away, or if file names change, that means you've got to go back into your code and edit that as well. That's kind of annoying. In tutorial 8, we briefly saw a more efficient approach for reading multiple sound files involving iteration, and we're going to revisit some of those ideas now. But there's a slight difference. In tutorial 8, we dealt with one single folder containing sound files, but here we have 3 subfolders, each containing audio files, all contained within a single parent folder. So although, yes, we could just dump all these audio files into one big SuperCollider array, we would lose our nice organizational scheme. And so instead, what I'd really like to do is mirror this organization of folders in SuperCollider. And to do that, I'm going to use a class called Dictionary. Dictionary and array are both types of collections used for storing multiple things, but the difference is that array is an ordered collection where each item is stored according to an integer index, and dictionary is an unordered collection where each item is associated with a unique name. I think dictionary is a more elegant and intuitive choice for buffer management because it enables us to refer to things by name rather than some number. So, for example, if B is our parent folder, then B at Shakers is considerably more meaningful than something like B at 2. Here's the essential syntax for creating and filling a dictionary. We start with a new dictionary, and to fill the dictionary, we use the add method, providing a name as a symbol, followed by this hyphen greater than construction, which looks like a little arrow, and the value we want to associate with that symbol. So in this case, we've stored 2 integers in this dictionary, 10 and 20. Integer 10 is associated with the symbol foo, and 20 with bar. So now, if we evaluate D at bar, SuperCollider returns 20. With that basic introduction out of the way, let's remove our buffers from the server and start fresh by creating a new dictionary. So here's what I'm envisioning. B, our dictionary, will represent our parent folder, buffers. And so B will contain 3 arrays, each representing a corresponding subfolder. And each of the 3 arrays will be associated with a symbol determined by the name of the corresponding subfolder. So when we're done, the code B at Shakers at 0 will refer to the first sound file in the Shakers folder, right here. And B at Crotales at 2 will refer to this file over here, etc. So the first thing we need to do is grab the path to our parent folder. And what we have here is just a plain old string. And as such, we can't do very much with it, but we can create a new instance of path name, which provides us with an arsenal of useful methods for accessing files and folders. The entries method, for example, returns an array of path names corresponding to the items inside the parent folder. As expected, there are 3 entries. And here's where iteration comes into play. We're going to use do to iterate over these 3 subfolders, and on each pass, evaluate a function with an input argument representing the current subfolder. Each time this function gets evaluated, we want to add a new entry to the dictionary, and we want to use the name of the subfolder as the associative symbol. And to do this, we take our subfolder argument .folderName .as symbol. And then stored at this symbol, we want to fill a new array with buffers using the sound files in the current subfolder. And array.fill needs to know the desired size of the array, in other words, how many audio files are in this subfolder. So we can just say subfolder.entries.size, and then a filling function, which is evaluated some number of times, determined by the declared array size. And all we need to do in this filling function is declare an argument, which will represent the integer index of each audio file, and then finally, read an audio file into a buffer. And to get the proper path name for each sound file, we get the subfolder entry at index I, and this will read each audio file one by one in, I believe, alphabetical order into the array. And then we also need to use the full path method, which is going to convert an instance of path name to a string representing the absolute path to the file. And that's it. So let's evaluate. So having done that, now we can see that B is a dictionary with size 3, as we would expect, and the 3 symbols in this dictionary have been generated according to the names of our 3 subfolders, which means we now have a unified, organized collection of sound files, which we can access easily and intuitively. For example, here's the crotale file at index 0. Here's one of our crotales on the break drum. Here we have a few desk bell sounds. And here's some of our short shaker samples. And just to reinforce the organizational mirroring here, back on the desktop, here are the shaker sounds with index 2, 3, and 4. So if we revisit our previous sound example, our sustained shaker sounds have index 5, 6, and 7. So we change the buff argument to ask for B at shakers at a randomly chosen index from either 5, 6, or 7. And let's not ignore the fact that we can use this synth-dev to play any of our sound files now that they're all loaded onto the server. So here's a crotale sample starting at the point where it's sort of rattling around noisily on the break drum. And here it is transposed down 1 octave. And let's create 5 synths at once with slightly varying start times and slightly varying playback rates. This gives us sort of a chorus effect. Okay, so regarding this nested iteration buffer reading code we just created, if you consider yourself to be sort of new to programming or new to SuperCollider, I could definitely understand if this just looks sort of really confusing. And on first glance, it's probably not the easiest thing in the world to digest. But if it doesn't make total sense now, I would suggest going over this part of the video a few times and trying it out for yourself with a similarly structured collection of your own sound files. And I think you'll find that this kind of approach is really very preferable to writing out 20 or 30 buffer.read statements. And keep in mind, a maybe not so obvious benefit to this approach is that on your hard drive, you can add sound files, remove sound files, change file names, even add more subfolders. As long as you don't change the name or location of the parent folder, this code will work like a charm every time. And even if you do change the name or location of the parent folder, you only have to change this one line of code. And believe it or not, there's even a way around this problem, which we're going to see in the next video. Okay, so moving on. Let's make another synth-def. The two that we already have both generate a signal, so let's make a synth-def that processes some input signal. And specifically what we're going to do is make a reverb effect from scratch. So first, let's take a brief moment to talk about what reverb actually is. Reverberation is the result of sound waves propagating in an enclosed space, primarily reflecting off the walls, the floor, and the ceiling, and all these different reflections reach our ears at slightly different times, but usually they fuse into one big reverberant sound that's audible for 1 or 2 seconds or something like that, depending on the space. So from a signal processing point of view, we can think of reverberation as the sum of many different feedback delays, in which the delay parameters are determined by the size, the shape, and building materials of some imagined indoor space. So in most reverb effects, there's a so-called dry signal, which is the unprocessed input, and the wet signal, which has the reverb applied to it. So we're going to declare two variables called dry and wet. And I'm also going to need a third variable, which I'll call temp. And this is going to be sort of a temporary signal which gets overwritten several times in succession as we create the delay lines and sum them together. And we'll also declare a fourth variable called sig, which is going to be our true output signal, some balance between dry and wet. And now we're going to get into some topics which we covered in tutorial 7, involving buses and passing an audio signal from one synth to another. We first establish our dry signal using in.ar, which reads an input signal from some audio bus. We'll give it the argument name in. And we'll deal with actually reserving an audio bus a little bit later on. And we also need the number of input channels. And for this, we specify 2, because so far all of our source synth-defs are stereophonic. And we'll also read this input signal into temp, so we have 2 copies of the same thing. And we're going to do all sorts of operations with temp, but we're going to leave dry alone so that we can mix it back into the output later. And wet is going to start as digital silence, so we're going to initialize it to 0. Otherwise, it has a value of nil, but we need wet to have some value so that we can do mathematical operations with it. And technically, we have some alternatives here. We could initialize wet to be like a DC offset of 0, or the very fancy silent UGen, but that's kind of gratuitous. 0 is fine. Okay, and most reverb effects also have something called pre-delay. This is the amount of time that elapses between our perception of the so-called direct sound, or the sound that travels in a straight line from the source to our ears, and our perception of the first audible reflections, usually where a sound is bouncing off 1 or 2 walls and then hitting your ear. And of course, this is going to depend on where you're sitting relative to the source in this theoretical space, and how big the space is, and so on. But I don't know. I guess 0.1 is sort of a reasonable value. But you could definitely experiment with making this value a little bigger or smaller if you want. So now we're ready to start creating and summing a bunch of feedback delays. So we're going to rely on yet another iterative construction using our good friend do. And I've settled on 16 feedback delays, but it doesn't have to be 16. You can definitely play around with this number. And inside our iterative loop on each of these 16 passes, we're going to send temp through a UGen called allPassN. And an allpass filter is basically a delay line with feedback. The N stands for no interpolation applied to the delay time. And there's also allPassL and allPassC for linear and cubic interpolation. But no interpolation is not only the most efficient of the 3, it's also totally fine in this case, because we're only going to be dealing with fixed delay times. So no interpolation is necessary. So sound travels pretty fast, so reflections in a closed space are usually pretty quick. So we're going to give our all-pass filter a maximum delay time of 50 milliseconds. And for our actual delay time, we're going to choose a unique stereo pair of delay times on each of these 16 evaluations, somewhere between 1 millisecond and 50 milliseconds. And the fourth argument for all pass is the decay time. And essentially this is our reverb time. And I'm going with the default reverb time of 1.8 seconds for no particular reason. So feel free to change this value. In a lot of real-world cases, high frequencies tend to get absorbed more quickly than low frequencies, especially with things like carpet and curtains and other soft, squishy materials. So using a low-pass filter can help simulate this effect and give more emphasis to lower and mid-range frequencies. In reverb software, this is often called damping. And so here I'm going to set a cutoff frequency of 4,500 hertz. And for the last step in our loop, we're going to add this temporary delay line to our wet signal. So these three things happen 16 times in a row, and at the end of it, wet is the sum of 16 low-pass filtered stereo feedback delays, each with a uniquely generated and considerably short delay time, and each with a 1.8 second decay time. After closing out this loop, we're going to use Xfade 2 to blend between the dry and wet, just like we did with the previous synth-dev. And again, use our ×2 - 1 feature so we can specify a mix value between 0 and 1. And here I'll also apply a master amplitude argument. And probably we won't ever adjust this value, but it's never really a bad idea to have the option to just shut something off completely. And we're done. So output the signal, close the UGen function, and add the synth-dev. Okay, so to put our reverb into action, we should reserve a 2-channel audio bus, because that's the kind of signal we're going to be generating. And that's done with bus.audio, providing the name of the server and the number of channels. And then let's instantiate our reverb instrument, making sure to use our new stereo bus as the input. And there it is on the node tree. And for a source sound, let's just do a short shaker sound with a little randomness in release time and playback rate. And by default, the output bus is 0, which bypasses the reverb completely. But if we send our output to the reverb bus, we hear reverb. So just to revisit a few ideas quickly from tutorial 7, whenever one synth is passing a signal to another synth, the sending synth must be above the receiving synth in the node chain. So here I'm taking advantage of the fact that whenever a new synth is created, by default it gets put at the top or head of the node tree. And since I created the reverb synth first, everything created after it will conveniently always be placed at the head of the node tree, and therefore above the reverb synth. And that's exactly what we want. If these ideas are sounding unfamiliar to you, then I would encourage you to go check out tutorial number 7. So here is a pattern, really quick, using our short shaker sounds and a little bit of randomness. And remember that all these arguments, including the output bus, can be subject to pattern control. So with something like this, we can randomly cause some synths to bypass the reverb. To make this effect even more audible, let's crank up the mix on the reverb synth. If you're like me, you will invariably hit Command period. Okay, seems fine. The sound has stopped. And let's say we want to go back to our original pattern where all the synths go through the reverb. So play this p-bind and we hear nothing. Of course, this is because Command period doesn't just stop one pattern, it stops all patterns and frees all the synths from the server, and that includes the reverb. So initially you may think, well, that's dumb. Now I have to reinstantiate the reverb every time I hit Command period. And while, yeah, that would work, it would also be really annoying, which is why there's a very good solution to this issue, and it involves the use of a class called server_tree. Unlike a lot of other objects in SuperCollider, you don't create new instances of server_tree. Instead, server_tree acts like a sort of one-stop repository where you can register one or more functions to be evaluated whenever the server is reset to its initial state. And this is a perfect tool for automating certain processes that you want to happen whenever the server gets cleared, like, for example, instantiating a reverb effect. So let's make a function called createReverb, and what this function is going to do when evaluated is just create one instance of our reverb synth. And then we register this function by adding it to server_tree. And so now, whenever we press Command period and watch the node tree here, this reinitializes the server, which is server_tree's queue to evaluate all of its registered functions. And this means a new reverb synth is created for us automatically. So now we can play our p-bind again. Wonderful, we hear sound. And just to show this off again, I'm going to hit Command period, and this does stop the sound, but also invokes server_tree. And so a brand new reverb synth is created and ready and waiting for us. And so if you ever want to remove all the registered functions from server_tree, you can just type server_tree.remove all. And now, hit Command period, and our reverb synth is no longer automatically created. That's it for tutorial 16. In the next video, we'll more or less continue from here and close out this 3-part series, introducing a few more concepts and getting into some more details. We may add another synth or two, I'm not sure yet, and we're going to revisit server_tree as well as its partner classes, server_boot and server_quit. But mostly we're going to focus on putting all these elements together and building an environment involving a sequence of musical event functions that provide a means of performing a short composition. And until then, I hope you enjoy playing around with what you've seen in this video and maybe developing a few synth on your own. So thanks for watching, and see you next time.